So there are a couple of things that I would like to do today, and one of them is I want to discuss a little bit more about the coexistence of phases. Okay, so different phases, for example, liquid and gas, solid and liquid, and so on and so forth. And also talk about what happens in the so-called supercritical liquid region, when the temperature is higher than the critical temperature for coexistence, and therefore, if we can talk about the liquid, the gas. And the other thing I would like to do is to discuss a little bit more about thermodynamic inequalities, and how to obtain, for example, some inequalities, simple inequalities that say things that should be obvious, but it should be obvious in the sense that we witness them in everyday life, and in the experiments, like for example the positivity of specific heat, constant volume, these sorts of things. Okay, but before I do that, if you have any questions, or if you want me to clarify a little bit, clarifying means adding details, not asking me to repeat what I have already said 1 or 2 lectures ago. So, are you working out problems or examples on how to calculate the work done in a cycle, the heat exchange? Have you done this by yourself? So I used to call people at the blackboard for during lectures, but I don't think I will do it because I don't know who of you have signed or not your right to be filmed. Okay, so this has to be left for the teaching assistant to do. But if you have any questions, or if you don't feel like I gave enough details about the topics, some of the topics covered, you should ask me. Okay? I can spend an extra 5 minutes or 10 minutes on something. I mean, it's more important that we understand what we have been talking about in class rather than keep adding concept after concept. Any questions? Nothing? Okay. So the thermodynamic potentials that we have introduced yesterday, free energy and enthalpy, they are useful because they are very useful in calculations, and both for simplifying things. I mean, they are not independent concepts. The only independent concepts are internal energy and the entropy. Okay, and all the other concepts like the free energy, the enthalpy, they are more natural in some setups. Okay, so when we talk about the system, so we define the free energy as the quantity that gets minimized in a irreversible transformation when the system is at constant temperature. Okay, so it can exchange heat with the environment, and its temperature remains constant. The same for enthalpy, or what we call phi. Which gets minimized in processes, in irreversible spontaneous processes which occur at constant pressure and temperature, okay, not constant volume and temperature. So in the enthalpy, we allow the system to do some work because constant pressure does not mean constant volume. So if the volume expands, you're doing some work, PDV. Okay? But they're not, these concepts are not, they are not more fundamental than internal energy and then the entropy. And in fact, we follow the logic of the construction of thermodynamics, introducing the internal energy with the first law, the entropy with the second law, and then after 4 or 5 lectures, we have introduced the free energy. Okay. But as I said, if we talk about a system, if we talk about transformations that occur at constant pressure, which is the more common situation, like transformation that occurs, for example, when you boil water, a pot of water in your kitchen, that's a transformation that occurs at constant pressure, and the pressure is the pressure of the room, which is roughly 1 atmosphere. Okay? Depending on the weather, the pressure can go up or can go down. Like, for example, today I think it's pretty low, the pressure. In fact, we have clouds that have come in. And so the transformation occurs at constant pressure. And therefore, the natural concept to consider is the enthalpy. Okay. And that's what I want to discuss today. So I want to discuss transitions between phases. For example, transformation and constant P and T. In particular, today we are interested in phase changes. Okay? So, consider one substance in a single phase. An example. Can you give me an example of a substance which is in a single phase? Water, liquid water, for example. Or another example, a gas. Okay? So this is one substance which is in a single phase. We can have different components, okay, that occur in the same phase. For example, you can have, I don't know, hydrogen and oxygen in gas phase, but hydrogen and oxygen can mix and can form water. Okay? And if water is formed in the gaseous phase, we have one phase and 2 components. Okay, 3 components actually in that case, because we can have hydrogen, oxygen, and water. And so on and so forth. 2 phases, an example of coexistence of 2 phases, of one single component, for example. Water, ice, okay? Or another example, water vapor, okay? Something with, not with water, with something else. A saturated solution of salt, for example. In that case, the 2 phases are the little bit of salt here and the solution here. Okay? So in this case, you can have salt that goes in solution and gets back here. All right. So the general situation is that in which we have F phases and n components. Just a second. So each of the n components can be in one of the F possible phases. Okay? And therefore, the mass, there is a mass of component, let me use, of component 1 in phase 1, mass of component 1 in phase 2, the mass of component 1 in phase F, and so with the various masses that define our system, we can define what? A matrix. Okay, mathematics, such an array is called a matrix with two indices. One index defines the phase, and the other index defines the component. So here, for example, you can have salt in phase 1, which is solid, or in phase 2, which is the solution. Okay. Or, for example, we can have water, and we have gas here. Vapor, yes, vapor here. Steam. So the water can be either in liquid form or in gas form. So in this case, there are two phases and one component. Okay. So we have to write the enthalpy. We consider this transformation occurring at constant pressure. We define the enthalpy, and the enthalpy of the entire system, we assume is just the sum of the enthalpies of the various phases. Yeah, exactly. Okay. Each phase, the enthalpy of one phase depends only on the masses of the components in that phase. Okay, so here I should write something like this, actually. I should write 1, 1, and 1, 2, and 1n. Okay? This is an approximation. What am I neglecting in this approximation? Think about the simple situation, which is water and steam. I'm summing the enthalpies of the steam and of water. So F will be equal to 2, N will be equal to 1. Okay. What am I neglecting? I'm saying that I'm just adding the enthalpy of this system, the enthalpy of this system. And therefore, I'm assuming what? That they are not interacting, okay? But where is the interaction? On the surface, right? So I'm neglecting the surface interaction, which is captured by the concept of surface tension. Okay, so I'm neglecting the surface tension. So in this case, for example, in the case of water, I will have to write phi is equal to phi of steam, let's put vapor, okay, which is a function of pressure, temperature, and the mass of vapor, plus the enthalpy of the liquid, function of pressure, temperature, and mass of liquid. Yes?
If you need, when you use terms, if you need to find, because there I think...
Sorry, just a second. I made a mistake. There is an I here. It's not 1. Yes, so.
Find out that between chloride of sodium and water in the end of solution, how you can know it.
Say it again, sorry, what's the question?
There is water with chloride of sodium, okay?
With what?
Chloride.
Oh, with salt, with sodium chloride. Okay.
So when you use Enthalpy, you want to need after the solution,
Percentage?
yeah, after the solution, you need, because you will use Enthalpy, and then you will see the temperature in the end of your solution.
Okay, so let me clarify what I mean at constant temperature. It means that the temperature, I set the temperature. Okay? The experimentalist sets the temperature and sets the pressure. Okay? And the only variables that need to be found are the masses, the fraction of the masses of the substances, various components in the various phases. Okay? So the variable to solve for, when we can, it's this matrix. The pressure, the temperature, and the functional form of the enthalpies are fixed. Okay? You don't have to find the temperature afterwards.
But in equilibrium, which solution will stay after?
We have to solve that problem. The question is, what is the solution the amount of salt that is in solution? Okay? This is the variable to solve for in our problem. So what's the enthalpy? For example, let's consider this simple case here. Okay? In this simple case, we have steam, so this is gas, and this is liquid. So the enthalpy of a gas could be easily approximated by the enthalpy of an ideal gas. Okay? The enthalpy of the liquid is a little bit more complicated. But the thing that we can measure easily in the lab is when we change by a small quantity the mass of the liquid, how much enthalpy changes. Okay, because we have to measure how much. This is constant temperature, so it means that we are giving heat or taking out heat from the system, and you assume you can measure that. Okay. So, what's the condition for equilibrium? Equals 0 what? Enthalpy equals 0. Why? No. When it is minimum. And how do you find the minimum of a function? You take the derivative, and you put the derivative equal to 0. Okay? So we have done this exercise already, but let's do it again. So this means that there is a transformation in which some mass of the component K goes from phase I, so MIK goes to MIK minus delta M, and the same component K goes in a phase J. Okay, in this case, for example, we have mass of liquid decreases a little bit, but the mass of vapor has to increase of the same amount. Okay, so under this change, there is an enthalpy change, and we have to put this equal to 0. The vapor minus the M Okay, so in this example here, you see that the change is the sum of the changes of the two functions, but in one case the mass is increasing here. Sorry, we decided to change, so this is plus, this is minus. Okay, there is a little bit of liquid that goes into vapor. Okay, so this change is positive, is negative, minus delta M, and this change here is positive, plus delta M. This is equal to 0. This means that the derivative of the enthalpy with respect to the masses have to be equal. If we do this for the general formula, we find that the derivatives of the various phi I with respect to the mass of the component K have to be equal. Okay? And by the way, by using this equation, we had obtained an equation for the that connects the saturation pressure with the temperature in the, which examples did we do? I don't remember. We did some examples, like the solid that goes into vapor. And so because this is something you can measure in the lab, we assume it's a constant. Okay? And this is something which it's easily written because we know what the internal energy and the entropy of a gas are, or also what's the equation of state of the gas, and then we take the various derivatives. And we could solve this equation as a function of the pressure. Okay, by putting this thing here equal to a constant. You remember we had something like the pressure was proportional to e to the minus lambda divided by T divided by m, something like this. Okay, the constant in front could not be determined. It could be determined if we consider the constant in the third law of thermodynamics. Okay, so in this case, that set of equation is f minus 1 times n equations. Okay? And the number of variables is f is f times n minus 1. Why not n? Because only the ratios between the masses are important, because the total amount of mass is fixed, okay, for a given component. So only the ratios of the masses are fixed. Plus, so we have this number of equations, and we have these plus p and t. So plus 2 number of variables. So the variance of the system is the number of variables minus the number of equations. Because if the number of variables is equal to the number of equations, then we could solve, in principle, the equations and find a unique solution. If there are more variables than equations, there are parameters that we can set. Okay, so this is called the variance of the equation. And so this is f n minus 1 plus 2 minus 1 times n, which is equal to well, the number of equations is because this equation this equation has to be true for any component k. Okay, and so we have n times, and the number of equation for each component is number of phases minus 1. Okay, for example, if the number of phases is 2, you get 1. Okay? Yeah, you get 1, as we did before. If the number of phases is 2, vapor and liquid, then you have to consider the transition between vapor and liquid. Okay? If it is 3, you have to consider the transition between vapor and liquid and liquid and gas. Okay, so it's f minus 1. And this is true for any component n, so you multiply just by n. The number of variables is for each, for fixed phase, only the ratio of the masses is important. Okay, so the ratios are n minus 1. If you have n variables, you can make n minus 1 ratios. independent ratios. And you multiply this by f, and this 2 is just p and t. You have 2 extra variables in your equation, p and t. So for example, the simplest example. One phase, one component in one phase. Okay, then you have that the variance is 2. What are these 2 free variables that we can choose? Temperature and pressure. Right? The third variable, the volume, is defined by the equation of state. Okay? If n is equal to 1 and f is equal to 2, then we have v is equal to 1. We choose only one variable, and the other one is defined. Okay? So this is the case that I said before, steam and water in equilibrium. You can only choose the temperature, and the pressure is determined by one of the equations.
We can aim for three variables. Three or four.
Which variable?
You can say f n minus 1 plus 2.
Uh-huh.
If you can generalize plus n, maybe m variable, no?
No. I mean, this can be equal to any number you want, but you don't add here.
Just 2 variables.
Yes, because you only have pressure and temperature. So only 2 variables, pressure and temperature. You cannot define other things. I mean, for these systems we are talking about, if you are considering something that is not defined by pressure and temperature only, but you have to define, I don't know, total magnetization or total spin of your system, then you have to include other variables. But this is not the case we are considering. So this is not arbitrary. I'm just saying for any system that we are considering, this is always true. It's not. Okay? So, now let me discuss what happens for for water. So here we have ice, so solid. Here we have steam, so gas or vapor. And then we have point at which we can have liquid. And here we have the line between the solid and liquid. How do I have to draw this line? Like this, like this. The first one. Why? dP, very good. dP over dt is negative. And we say that it is negative. And so this one is the correct one. It's actually pretty steep because dP of dt is very negative. Because why is it negative, first of all? Say it again. is a signature?
Mixture of water.
Yes, but we had an equation for dP by dt, right? What was the equation for dP by dt? dP by dt was equal to lambda over the, what was it? V liquid minus V solid times T. Okay? So this is the inverse of the density of the liquid, and this is the inverse of the density of the solid. So if the solid is less dense than liquid, this is larger than this, and so we get a negative sign. So for water, we have this line. There are a few other substances which have dP by dt negative at the solid-liquid transition, but most 99.9% of other materials have this line like this. Okay? So let's go on this diagram. Actually, at a certain point, this line changes and does like this. Because you might know, but there are many different kinds of ice. There is not just one, depending on the structure, on the crystalline structure that they get. You can have ice 1, ice 2, ice 3, ice 4, ice 5. So at a certain point, there is a phase in which it's more convenient. So the lowest enthalpy state is another form of ice, which is more dense than water. And so the shape changes. Okay. So there are, if you want here, there are two kinds of ice. There are many kinds of ice. I'm not drawing all the diagram also because I don't remember it by heart. So there are many kinds of ice here. But at a certain point, there is another critical point after which a new kind of ice enters into the game, and this line goes in this direction. Okay? So this point here, do you know how it is called? 3 critical point. And for water, so first of all, this kind of point exists for all substances. There is a point around which solid, liquid, and gas, for phases of the substance, actually coexist. Okay. For water, the temperature is essentially 0 Celsius, but the pressure is very small. It's 6 times 10 to the minus 3 atmospheres. So now, if this thing here is way up. Okay, so let's forget it for a second. Let's assume that in our scale, this point is at infinity. So if this is some sort of logarithmic scale, let's assume that 1 atmosphere is here. And so at 1 atmosphere, we go from solid to liquid to gas And as I said, this line is pretty steep. Why is it pretty steep? Because the densities are very close to each other. So this derivative is very large. So the first, so if at 1 atmosphere water freezes at 0 Celsius, this means that this is not really 0 Celsius, it's slightly larger. And in fact, it's something like 0.007 Celsius. This is more like 0 Celsius. And this point here is which temperature? 100. Okay. So you see, if you lower the pressure, what happens is that if you lower the pressure, what happens is that at a certain point you don't go through the liquid phase. Your system goes from solid to gas directly. If you increase the pressure, your system always goes from solid to liquid. But then there is a point at which the liquid-gas transition is not a phase transition anymore. So above this point, your system goes to from liquid to gas without boiling, in some sense. There is no difference between liquid and gas. This line here, so let me explain. So what does this line here? Oh, so first of all, so this kind of system, which we have one component and two phases at any of the 2 points, at any of these lines, is called univariate. It has only one. V is equal to 1. There is only one variable, okay, which has to be fixed. So, for example, if you fix the temperature, you fix the pressure. At this temperature and this pressure, there is coexistence of liquid and gas. What if F is equal to 3 and N is equal to 1? Then V is equal to 0. It means there is no variable free. And in fact, in this diagram, there is only one point. So there is no variable that we can choose, like the temperature. We cannot choose the temperature. The temperature is fixed. The pressure is fixed, too. So there is only one point. So you see, this simple equation counting is very powerful. It tells us that there is only one point in which a substance can exist in 3 different phases. We cannot, there is no free parameter. We cannot choose anything. And moreover, it tells us that there are lines that divide 2 different phases of a given substance. Okay? Is it? Yes. Okay. I'm coming back to that. I just wanted to make clear this thing that I have overlooked for a second. I just want to make clear that if you consider the solid-gas transition, there is a line. If you consider the solid-liquid transition, there is a line. If you consider the liquid-gas transition, there is a line. So a one-dimensional object. Okay? If you consider the coexistence of solid, liquid, and gas, there is a point, zero-dimensional object. All right. So, and also the other thing that I wanted to show, to stress is that the derivatives of dp by dt are positive on the other two lines, because the only anomaly is the difference in the density of liquid and solid. It be, in this region here. The gas and liquid is very the gas and liquid. The gas is much less dense than liquid here, around here. So the slope you see goes like this, very very small. Because the larger this difference, the smaller dp by dt. And the same between solid and gas. Yes.
Is it possible to pass directly from solid to gas?
Yes. The question is whether it's possible to pass directly from solid to gas. Yes, here. If you are at sufficiently low pressure, say 0.1 times 10 to the minus 3 atmospheres, then you are down here. You go from solid to gas. Constant temperature. Constant pressure, you increase the temperature, and you don't generate any liquid, just your piece of ice just evaporates. Okay. There are substances for which these points are at very high temperature, so we never see liquid form of these substances. We just see transition between solid and gas. We made the example of naphthalene, right? That you put a piece of this thing, and that just evaporates in your closet. Okay, let's discuss this point here. So this point for water is at 374 Celsius. And at a pressure of around 280 atmospheres. So this means that if we go to higher temperature, the transition between gas and liquid is not of the same form as we have seen below this temperature. So there is no boiling, there is no coexistence of liquid and gas. The system just smoothly goes from one phase to the other, without any phase transition, without. Have we seen something similar during these lectures? In another, in one example of something that was solvable that we gave. That above a certain critical temperature, nothing happened. Below a certain critical temperature, there was passage. What did we see? Clapeyron equation, but that's for the van der Waals gas, right? In the van der Waals gas, we have a very similar behavior. So in the van der Waals gas, if the temperature is very large, the isotherms are pretty smooth. Okay. And then there is a critical temperature at which there is a change in the behavior of the function, right? There's a change in the behavior of the function, and below this, we can have coexistence of liquid and gas. Okay, so how do we find this? So let me write. The equation. So how do we find this point here? So the point here is found by taking. So the function here is monotonic, and here is not monotonic anymore. Below goes down, then up, then down again. Okay. Then we find this point by taking dp by dv is equal to 0, and d square p by dv square is equal to 0. So both the first and second derivatives of the pressure vanish. So we have three equations, 1, 2, and 3, and we can solve for the three variables. Okay. So this point, so there is a critical pressure, which you can find by solving the equation. It's A divided by 27 B squared. A critical volume, which is 3 times B. And a critical temperature, which is 8A divided by 27B times R. So if we increase the temperature at constant volume, we see that we have liquid and gas. So we have liquid and gas. There is some quantity of liquid, some quantity of gas here. Then you keep increasing the temperature, and at a certain point, when you approach this critical point, gas and liquid are not distinguishable anymore. And in fact, if you do the experiment, you don't see the line that separates the two substances anymore. The liquid and gas have the same density, and they look exactly the same. So they mix into each other, and you don't see the difference anymore. Okay? If you lower the temperature, then at a certain point, you have to return to this situation. And so suddenly, when you pass this critical temperature here, they phase separate, because liquid is more dense, denser than gas. So the gas goes up. So there is a transition in which there are a lot of bubbles, and then they phase separate again. So there is a very nice video on YouTube posted by a professor in Nottingham that does this experiment on sodium hexafluoride. And you can where this critical temperature. So you see this critical temperature in water is 374 Celsius, and the pressure is really high. 280 atmospheres. In other substances, the pressure and temperature are much smaller. For example, in sodium hexafluoride, the critical temperature is around 50 Celsius. So I wanted to show you. I wanted to show you the video on YouTube. Can I use the computer? Yeah. It's off. Have you ever seen such an experiment done? It's very easy, actually. Aspetta, così faccio vedere sta cosa. Troppo mi sono scordato il portatile. Tanto abbiamo tempo, comunque. Sì, sì, sì. Piuttosto che fargli tutte queste disequazioni qua, faccio vedere il video. Oh, critical error occurred. Okay, interesting. Sorry, but I forgot my laptop at home, so I had to bring my laptop. I had prepared it on my laptop, but I realized before that I didn't put it in the bag. But it's on YouTube. So did you find it? While that's loading. So if you find the critical, no critical temperature, no, the critical point SF6. What's going on here? Okay. Let's see if I can find it. Yeah. Sulfur hexafluoride. So you see, so when you increase the temperature, let me actually. Okay, let me start from the beginning. So you increase the temperature, and your system starts boiling. Okay. Not only, but notice also that the line moves towards towards up, moves up, okay? Because the liquid becomes less dense when you increase the temperature and presses on the gas. And then, at a certain point, the line disappears. There is no difference between the liquid and gas at this point. They are the same thing. Okay, so we are in the part of the phase diagram in which there is no phase transition anymore. Okay, so you keep, yeah. Okay, so now if you lower the temperature, the gas and liquid were mixed, but when you lower the temperature, the density of the liquid becomes larger than the density of gas, and therefore, by gravity, it goes down. If there were no gravity, you would not see this burst. By gravity, at a certain point, the liquid density grows a lot, so the liquid goes brown, and the gas is pushed up, and you see. This is by lowering the temperature, and then you return to the original. Okay, let me show you again. So the line moves up, the liquid starts boiling, and at a certain point, there is no difference between liquid and gas anymore. You don't see any difference. And then you start lowering the temperature, and again, boom. What do you think? Is this transformation reversible or irreversible? It's irreversible, right? Okay. Yeah, this is what I wanted to show you rather than. Okay. Yes. So is this state a new form of matter? No, I wouldn't say so. It's simply a supercritical fluid. It's something that is a gas and a liquid. There is no. If you do the transition, if you move your parameters slowly to go around this critical point here, okay, you go, for example, to small pressure, high temperature, then you increase the pressure, come back. Okay, you would not see any phase transition. Okay, everything will turn into liquid without having anything. I mean, this bursting, this sort of here you're actually passing through. You're cutting through the critical point, and there is gravity, so you see this burst here. But otherwise, you can see things moving smoothly. You can turn gas into liquid by doing this thing here and never having to change phase. Okay, so it's not a new phase. Okay. All right. So I think we can turn this off and we can resume the lecture. Come si? Questo perfetto. Okay, so I think I will can also probably stop here. So I wanted to show you. Yeah. Uh-huh. Okay, so the question is from the formulas, how can we see that this stops at a certain moment? Well, if you look at the formula here, okay, the question is the following. Do you see a change in behavior of the pressure as a function of volume? Yes, you do. Okay, so again, as an exercise, you go home and you solve these three equations for three variables, P, V, and T. 1, 2, and 3 equations. Okay? These are a bit of complicated equations because this is a cubic equation for V. Okay? But if you put it in a computer, you can solve it very easily. But or what I suggest is actually that you do it by yourself because it's not so complicated after all. And moreover, there's only one solution. Okay, there's only one, so there's a unique solution, and this solution is the one that I just wrote here. Above this temperature, 8A divided by 27B times R, there is no, the curves are smooth and going down, so if you follow this equation for temperature higher than this thing, you should not see any discontinuity, any change in the derivatives, and so on and so forth. So you should assume you are in this region here. Okay? Very high temperature, and you decrease the volume, so the pressure increases. Okay. Other questions? So if you, as I said, if you go on YouTube, there is a series of videos on this critical point, and there are also explanations for the particular experiment. For example, this that I showed you was on sulfur hexafluoride, SF6, which is easy to, the experiment is easy to do because the critical temperature, as I said, is about 50 Celsius, I don't remember. Might be 45, might be 55, I don't remember. Okay, and but there are also other experiments done, and actually these things are, I mean, these critical points are very useful in engineering. I think in spacecrafts and the space shuttle, I've read somewhere, but I will have to check. But this is for you to check, actually. Go and see if this is true. The gases which are used, so there is oxygen, there is hydrogen, I think, that they are used to do the reaction that then generates the flame, and they are kept at the tricritical point. Okay, in the supercritical region, because they are easier to, because it's easier. I think the reason must be that it's easier because since they have the same density. Okay, so when the rocket moves, you don't have water, you don't have the liquid that does like this. So it's easier to. So this is the reason that I think it's underlined. But if you do a research and you tell me why, these things are on the web. Anyway. Okay, so let me stop here.